So electrochemistry, like so many other things that we do in this course, is such a larger topic that we're barely going to scratch the surface of it. So let's just jump right into this and get going. Now, all electrochemistry reactions are what are called oxidation reduction reactions, or sometimes deemed redox reactions. So redox reactions just refer to how substances gain or lose electrons. Now, I know up until this point we've been talking about atoms and molecules and moles governing reactions, but in reality it's actually the electron movement. And I hate to say this, but kind of what I've been teaching you is a little bit not so much the truth. It's just that there are many layers to the onion of chemistry, and this is just one of those core layers that we haven't quite gotten to yet. You know, remember that bonds are all related to electrons, and if things don't bond, then they don't form reaction. They don't form compounds, and if compounds don't form, then reactions don't occur. So in reality, we're really talking about electron movement more than anything else. Now, in order to understand how the electrons move, which we'll get into the next podcast, we've got to talk about oxidation numbers. Now, oxidation numbers are a method of tracking the electrons gained or lost. So there are 4 rules that govern how to determine whether or not something has an oxidation, or what something's oxidation number is. So, rule number 1 is the oxidation number for an element in its elemental form is 0. For example, hydrogen gas. Notice the diatomic. Hydrogen gas would have an oxidation number of 0 because that's in its elemental form. Oxygen gas, carbon solid, bromine liquid are all elements in an elemental form. If I gave you a situation like diatomic bromine, but I said gaseous diatomic bromine, well, this is not in its elemental form, so it would not have an oxidation number of 0. So state of matter is only important when doing oxidation numbers and when trying to figure out if something is in its elemental form. The oxidation number for any monoatomic ion is its charge. Now, remember, mono means 1. So we're looking for an ion that only has 1 atom in it. This would be things like Cl-, sodium+, lead-2 are all monoatomic elements. Monoatomic ions. So therefore, the oxidation number of chlorine would be -1. The oxidation number of sodium would be +1. The oxidation number of lead will be +2, so on and so forth. Okay, it's very straightforward. These first 2 rules are no-brainers. So, rule number 3. The more electronegative atom will have an oxidation number equal to its charge as a monoatomic ion. Oh my goodness, that's a lot of words, but actually it's not that complicated. Let's go back to our periodic table notes and look at electronegativity. So this is a chart of electronegativity. Now remember, electronegativity is how much an atom wants to gain an electron. Not lose an electron, but gain an electron. So you'll notice that the halogens are some of the highest ones because they have some of the highest values because they really want to gain the electron to fill the octet to become more like the noble gases. You notice things like the alkali metals have the lowest electronegativities because they don't want to gain electrons. They want to lose electrons. And electronegativity, as you can see, increases as you move up and to the right on the periodic table, with fluorine being the highest. So if you're looking at a compound and you're trying to figure out which one will want to gain an electron most, you just have to think about which one is closer to the upper right side. You don't even have to know why, you just have to know closer and upper to the upper right corner, and that's the one that's going to be the most electronegative. Now, so let's go back to something like sodium chloride. Okay, so now we have a compound, and we look and we say, okay, which one's the more electronegative atom, sodium or chlorine? Well, chlorine is the most electronegative atom, so therefore it will take on the oxidation number equal to itself as a monoatomic ion. So chlorine would have an oxidation number of -1, and sodium would have an oxidation number of +1. And you're like, wait a second, Mr. Siegel, how did you figure out that sodium is +1? Just wait 1 second and I'll get to, let me do one more example and then I'll get to the last rule. And then if you looked at a compound like, let's talk about lead-2 oxide, so PbO. Well, oxygen is the more electronegative atom, and its charge as an ion is -2, and therefore that would make lead plus 2. This is how you can figure out what the Roman numeral is on an atom too. If you don't know, like if you don't remember how many Roman numerals it has, like plus 2, plus 4, etc., then you can always do the oxidation numbers and figure it out from there. And then the last rule, and this explains how I got the sodium and the lead, is the sum of the oxidation numbers must equal the overall charge on the compound. So if you look at the overall charge on sodium chloride, it is 0 because there's no charge up here. And the same thing with lead. There's no overall charge like a polyatomic ion would have. Therefore, the overall charge must be 0. So once I knew 1, I could balance it out. For example, let's do something more complicated. Let's do sulfate. Now, some people are like, well, where did this -2 charge come from on the sulfate? Well, this is where the -2 charge comes from, is its oxidation numbers, how many leftover electrons it has. So I look at sulfur and oxygen and I say, okay, oxygen is the more electronegative atom, therefore the oxygen will be -2. Now, there are 4 oxygens in this compound, so that makes it 4 times -2, which would be -8. Okay? Now, I kind of treat this as I'm trying to figure out what the sulfur would be, like an algebra formula. So I say sulfur plus that -8 of the oxygen is equal to an overall charge of -2. Therefore, sulfur must be, please tell me you're not pulling out your calculator right now, sulfur must be plus 6. Mental math, people, mental math. Okay? And that's what ends up happening, is when the oxidation numbers don't balance, that's when you get the charge left over of for your polyatomic ion. So here's some chemical reactions, and it says identify the atoms that undergo a change in oxidation state. Now, not everything will undergo an oxidation state change. Usually one thing will gain electrons and one thing will lose electrons, and I'll talk about that more in the second podcast. So let's go through and identify them individually. So I've got 4 atoms that I could have. I have P, Br, H, and O. Those are the 4 elements that are on the left-hand side and obviously repeated on the right-hand side. So let's start with the easy ones. So let's start with oxygen. Oxygen is the more electronegative atom. It's going to be -2 here, meaning that hydrogen will be +1 to balance it out. And the reason I say +1 is there are 2 hydrogens, and if I solve it, I've got, 2 hydrogens -2 is equal to 0. Solve for hydrogen. Hydrogen must be +1. So that's on the left-hand side. I look at hydrogens on the right, and I say, okay, well, bromine is the more electronegative atom here, so it's going to be -1, meaning hydrogen will be +1. So hydrogen did not undergo a change. Therefore, I don't have to worry about it. Oxygens, in this one, oxygen is the most electronegative atom. It is -2, so it went from -2 to -2, so I don't have to worry about it either. I know I'm going a little fast. It's okay. This is not hard. This is about practice. The more you practice it, the easier it is. So now let's focus in on the phosphoruses and the bromines. Now, I've already identified the fact that bromine is -1 on this side. So let's look at it. So it went to a -1, but what is it on the left-hand side? Well, okay, so in PbBr3, bromine is the more electronegative atom. Therefore, it was started off as a -1 charge. Therefore, it ends as a -1 charge. And if you don't know, just go back in the podcast until you get to the electronegativity chart and look at the electronegativity chart, or pull one up on the internet. It's really easy to find. So bromine went from -1 to -1. Now, let's look at the phosphorus. The phosphorus is going to be the complicated one. So here, I have 3 Brs, which would give me a total of -3 for the Br, meaning that phosphorus must be +3 to start. Now I come over to the other side, and I say, okay, well, the oxygens are -6, because there's 3 of them, and they're each -2. Hydrogens are +1 each, so that gives me a +3 hydrogen. So I've got 3 plus phosphorus -6 is equal to 0, meaning that phosphorus must be +3, and guess what? Nothing underwent a charge in this first one, so your answer would be none. And you're like, Mr. Siegel, are you kidding me? Did you seriously just walk us through an example in which nothing changed? Yes, I did, because I wanted you to be able to see how the whole process is set up. Now let's go to this next one. So again, it really doesn't matter which one you start with. We've got sodiums, we have iodines, We have hydrogens, we have oxygens, and we have chlorines. Now, I'll tell you that hydrogen, 99% of the time, does not undergo a change, so I'm not going to really be concerned about hydrogen right now. I'm going to worry about all my other ones first. So I look at sodium and iodine. Well, iodine is the more electronegative atom of the two. Therefore, it will be -1 when it starts, and sodium will be +1. Now let's look at this second compound. So oxygen is the more electronegative atom than chlorine, so it takes on a -2 charge. Hydrogen is its typical +1, meaning that chlorine in this example must also be +1 in order to make everything balance out. Now remember, hydrogen can only be anything other than +1 if it's in its elemental form or it's as a hydride attached to a metal in its column. Now let's go to the right hand side. So oxygen again is the most electronegative atom at -2, so oxygen did not undergo any change. Sodium is going to be +1 because sodium only has two oxidation states, 0 and +1. Since it's not an element in its elemental form, it must be +1. And therefore, if you've got -6 and +1, that means your iodine must be +5. So iodine underwent a change. Your sodium went from +1 to +1, so it did not undergo a change. Now let's look at your hydrogen and your chlorine. Chlorine again is your most electronegative atom. It is -1. Hydrogen is +1. So hydrogen didn't undergo a change, sodium didn't undergo a change, oxygen didn't undergo a change, and chlorine went to -1. So those are the two atoms. Iodine went from -1 to +5, and chlorine went from +1 to -1. Okay, now this one looks really complicated, but it's not. It just has a lot of atoms. The process doesn't change. Sulfur, oxygen, hydrogen, nitrogen, and that's it. They're just repeated over and over again. So hopefully by now you're starting to see a trend in the fact that oxygen very rarely changes oxidation state. So let's focus in on these other things that do. So oxygen here is -2 each for a total of -4, meaning sulfur must be +4. Oxygen is the most electronegative at -2. Hydrogen will be +1. There are 3 oxygens, meaning there is -6 total. Hydrogen is +1, leaving you +5 for the nitrogen left over. And then this is your typical -2 +1 situation. Now let's go to the other side. H2SO4. Oxygen is -2 for a total of -8. Hydrogen is +1 for a total of +2, meaning that sulfur here, if you can do the mental math, is now +6. Because +2 +6 would be +8, balancing out the -8. Here, oxygen is -2, so again, oxygen did not change. Hydrogen also did not change, so we don't have to worry about it. And then nitrogen would be +2 to balance it out. So your two things that underwent change were your nitrogen and your sulfur. Now, notice that in this question it says identify the atoms that undergo a change in oxidation state. So the answer to this question is really just sulfur and nitrogen. But sometimes they say identify the ones that undergo change and their change. So make sure you do this whole process to figure it all out. And that's everything you need to know about oxidation numbers. In the next podcast, we'll get into like voltaic cells and all of that stuff.